Welcome back to Calculus 2. In this video, we're going to finish our discussion of power series by talking about Taylor and MacLaurin series. This is actually going to be pretty light on theory. We'll get into exercises pretty quickly. That's because usually you have to dig a little bit deeper before you get into the real weeds on the theory of Taylor and MacLaurin series, and we're just going to do the introduction. So here's definitions. If you have a function with derivatives of all orders throughout some interval containing a as an interior point, the Taylor series generated by f at a is this: the sum of the kth derivative of f evaluated at a over k factorial times x minus a to the k. And this equals... well, this is just showing you the term by term. Notice this is a power series. Just because it has this term, it just has a very specific formula for the constants. The constants are the kth derivative evaluated at a of the function, and then divided by k factorial. The MacLaurin series of f is the Taylor series generated by f at x equals 0. Because if it's generated by f at x equal a, it's x minus a. So at x equals 0, it's x minus 0. But note, all of these derivatives then are evaluated at 0. Sometimes that's very nice and allows you to come up with a pretty convenient formula for the coefficients. Sometimes not so much. So that's Taylor series and MacLaurin series. Then, if we have a function with derivatives of order k for k equal 1 up to n for some interval containing a as an interior point, the Taylor polynomial of order n, generated by f at x equal a, is the finite length polynomial. So the Taylor polynomial of nth degree, nth order, just takes basically the first n derivatives all the way up, including the 0th. So you could think of it as the sum, using our notation here, you could think of it as the sum k equals 0 to n of f to the k over k factorial evaluated at a, x minus a to the k, just like it says right there. Let's look at some exercises. So find the Taylor polynomials of order 0, 1, 2, and 3 generated by f at a. So we're looking at finding Taylor polynomial k equal 1, 0 up to n of fk evaluated at a over k factorial times x minus a to the k. So let's see here. We're going to need how many derivatives? We're going to need 3. So f prime of x is 1 over 2 square root x, I think. That's x to the 1/2. So f double prime is, let's see, that's 1 over 2x to the negative 1/2. So that'll be negative 1/4 x to the negative 3/2. And then f triple prime, so the third derivative, will be 3/8 x to the negative 5/2. So our Taylor polynomial, f, or p of 0, well, that'd be pretty simple. That's just the first term. That's the first derivative. So that's the 0th derivative, so the function itself evaluated at 4. So that's the square root of 4 over 0 factorial, which is just 1, times x minus a to the 0. So that's just 2. P of 1, that will be 2 plus the next term, which will be the first derivative, which is 1 over 2 times the square root of 4, so 1 over 4, then over 1 factorial, and then times x minus 4 to the 1, so p2, so that's 2 plus x minus 4 over 4. And then this will be 2 plus x minus 4 over 4 plus, let's see, this will be 3 factorial on the bottom, so, and then the second derivative will be to the 3 halves, so if you raise 4 to the 3 halves, it will be square rooted is 2, cubed is 8, so 8. And then this is also negative because of the minus, so we get a extra 1/4, don't we? Yep. So times 4, and then on top we'll have x minus 4 squared. So that's 2 plus x minus 4 over 4 plus, I'm tempted to write that as, I'm just going to keep the factorial. Oh, and this would be 2 factorial, not 3 factorial. 2 factorial. So that'll be x minus 4 squared over 32 times 2 factorial. Yep. Alright. P3, 2 plus x minus 4 over 4 plus x minus 4 squared over 32 times 2 factorial plus x minus 4 cubed over, now we're going to have the 3 factorial. Let's see what the other part's going to be. 3/8, huh? So 3/8 times 4 to the negative 5 halves. So that is, square root of 4 is 2 to the 5th. It's 32. So that's 3 over 8 times 32. Eight times 32 is, let's see, 64, 128, 256. Alright, so that's the Taylor polynomials of 0, 1, 2, and 3 at x equal 4. Alright. That will approximate this function. Let's find the MacLaurin series for this function. Now it's the MacLaurin series, and so the MacLaurin series is specifically centered at 0. So we need to look at the first couple derivatives of this because we have to come up with some formula now. Because they don't want the MacLaurin polynomial, they want the series. So if we think about f k of 0 over k factorial times x to the k. I guess I could use n there. Doesn't really matter. But it's n equal 0 to infinity. Well, let's see here. F of 0 is 2. F prime of x equals, let's see, 1 minus x bottom times the derivative of the top would be times 1 minus the top, 2 plus x times the derivative of the bottom, so that's times negative 1. over the bottom squared. So that's going to be 1 minus x plus, because negative times negative is positive, plus 2 plus x. 1 minus x squared. So that is 3 over 1 minus x squared. So f prime of 0 is 3. F double prime. Well, that's easier to deal with. F double prime of x that's 3 times 1 minus x to the negative 2. So that'll be negative 6 times 1 minus x to the negative 3 times negative 1. So that's 6 times 1 minus x to the negative 3. Evaluated at 0 will be just 6. F triple prime will be, let's see, 18 times 1 minus x to the negative 4th, which of course will be, will go to 18. And f fourth will just be 4 times 18, so 36, 72. 72 times 1 minus x to the negative 5, which should be 72. So, let's see here. I'm not having that much luck with the coefficient, with the derivatives. Maybe with the bottom I can come up with something? I don't know. It's 1 times 2. 1 times 3. 2 times 3. $18 is 2 times 3 squared. So 2 times 3 times 3. 72 is well, 2 times 3 squared times another 4, so 2 to the third. If you divide by the factorials, that's 2 over 1, so that's not going to do anything. 3 over 1, that's not going to do anything. 6 over 2, which is 3. $18 over 6, which is 3. And 72. 4 factorial is 24, I think. Well, I'm definitely seeing a pattern now. If I do one more. 5th. 5 times 72, I don't know, 5 times 7 is 35, so 350, 360. So if I did 360 over 6 factorial, let's see, that's 4 factorial, so 5 factorial, that'd be, yeah, it'd be 120, it'd be 3 again. Okay, so this would become the sum n equals 0 to infinity. Almost of this, it's not quite 3x to the n, because it doesn't work for the first term. But I think we can do it this way. Just make it go from the second term and then just add the first term in. So 2 plus n equal 1 to infinity of 3x to the n. Then we can use that as the formula. Alright. There's our MacLaurin series. I think I just got one more problem and we're done. I wanted to do a general Taylor series, not just a MacLaurin series. That's no different other than they just give us something other than a equals 0, so we'll see how we do with this one. So of course, if I plug in f of pi over 4, I will get cosine of pi over 2 plus pi over 2, which is cosine of pi, which is -1. Alright, f prime of x would be, let's see here, negative sine, and derivative cosine is negative sine, of 2x plus pi over 2, times the derivative of the inside, which is 2, so -2, f double prime of x would be, it's not going to change the sign, going to multiply by 2 again though, so -4 cosine of 2x plus pi over 2, and then f triple prime will be +8 sine of 2x plus pi over 2. F fourth derivative will be 16 cosine of 2x plus pi over 2. Alright then, starting with the even terms. Even terms are going -1. Well, let's see, maybe we'll get lucky and some will go to 0. If we plug in, we're plugging in pi over 4. So this will be sine of pi. Sine of pi is 0, so I guess that's just 0. Cosine, so that'll be back to -1 again, so that'll be +4. That'll be 0 again. That'll be -16. Alright, yeah, this will be a problem. Can really skip the 5th, so the 6th can tell pretty easily. It's just going to be times 4, so 64. -64 cosine of 2x plus pi over 2, which when you plug in, this really isn't equals. It's going to, when I plug in pi over 4, goes to +64. Yep. So with that in mind then, these are all just powers of 4, but they do have an alternating series aspect to them. So this is going to be the sum. You can keep the factorial on the bottom. N equals 0 to infinity. Just worrying about the powers, this would be 4 to the n, because that'll start off with 1, then 4, then 16, then 64. And then over n factorial. And then we need the alternating series part of it. So that's -1, although we want the first one to be negative, so we need to offset this by 1. So say n plus 1. And then we want x minus pi over 4 to the n. So there's the Taylor series. All we're using, again, is this formula. The sum n equals 0 to infinity of f, the kth derivative, the nth derivative of f, evaluated at a, over n factorial, times x minus a to the n. That's it for this video. Have a great day. See you in the next one. Next time, we'll probably start looking at some parametric equations. Go off in a whole new direction. See you then.